need to learn how to implement all these things. Okay. So next step, let me share. Okay. So now have you got an idea, right? So how the basic operations are performed. Okay. Okay. Now let me share. We'll go one by one. Okay. So this is the slide. So where we stopped, model building from scratch. Okay, this is done. Multiply, this is done. I think we have to start. Bias is also over. ReLU. Okay, so now here we have to start. So slowly, how to add a ReLU. Okay, so what is the forward pass? So we are multiplying the weights into input. That is the first step. That means this is the dot product. Collection of dot products, if you do over multiple patches of image, it will be convolution. Next, we are adding the bias. That is the second step. And as a whole, we are applying the nonlinearity. So here we studied what is meant by nonlinearity, etc. So while lectures in the further lectures, professors may explain deeper about nonlinearity. But as of now, nonlinearity is just another representation of the data. We apply some formula. Suppose C, ReLU of x equal to max of 0, x. That means if it is negative, I am taking only 0. If the input is negative, I am taking 0. And if it is positive, I am taking positive. Okay, so I have value. Suppose any negative value, I am mapping it to 0. And any positive value, okay, I am giving same. Okay, so my curve will be like this. Any positive value, okay, it will be same. But any negative value, I'm just starting it from 0. Okay, so next. So like this, 1 input, 2 input, 3 input, same thing. So I have an input, I have a weight, I have a yes, nonlinearity. Yes, Abdul. Nonlinear ReLU is meant for nonlinearity. So how this is how like it is just a striping of the negative values. Everything starts from positive values. Okay, 0 and positive. Yes, neural network can be able to see here is asking one question. Juhi Faridi. So what he or she is asking? Suppose see this was text data. Few may be numerical. So it is your responsibility. Suppose here features are there. So gender, female, okay, likes coffee or not. Yes, age 23. Suppose the feature is like this. When you want to feed it to the network, model doesn't understand any non-numerical values. So you have to convert that. So female. So male, you may take it as a 0. Female, you can take it as a 1. So you have to decide. So female 1, yes or no. So yes may be 0, no may be 1. So here it is yes. So it is 0. This is 23. So like this, all the non-numerical features by performing various techniques on your own, or you can use the existing functions, you can convert these features into non-linear numerical. Got it, Juhi? And about Abdul, yes, it will induce the non-linearity. Transformation is different. Feature transformation is different. Transformation means you are moving from one space to another space. That is different. Just encoding. Yes, encoding. Okay. One hot encoding. You have to encode. Okay, fine. So now output equal to, see here, input weight bias I have. So in weight into input or input into weight I am doing, plus I am adding the bias. And because it's a positive value, even if I apply ReLU also, I got 60. Same here. Now I have two inputs, two weights plus bias. Now dot product corresponding elements. So 2.0 into 0.4 plus, because I'm doing the dot product, 3.0 3.0 into 0.6. And then I'm adding the bias, ReLU, same value. Okay, so now let me show in the code. Okay. So this is all we are going to study by comparing everything. Okay. So ReLU started here. Okay, ReLU. Okay. So ReLU plus bias. See, this is the input. This is the weight plus bias. So input and weight, I am doing the dot product dot between input and weight, and then I'm adding the bias, and whatever I got, and I am passing to. See, ReLU is a built-in function. So TensorFlow dot neural network dot ReLU, it's available. So ReLU is a non-linear function. Whatever nonlinear, if you want to apply ReLU, you no need to write that logic max of 0, x, you no need to write. It's already available. So nn dot ReLU of y. So that is what the output. And I'm just converting into number. Same thing. This remains same. I'm adding the bias. ReLU is available. So that's why we have to use TF, TensorFlow or pyTorch. Same if you go to pyTorch also, if you see here, see dot product is there, torch dot nn dot functional dot ReLU. So inside functional dot ReLU, we have ReLU function. And here we have tf.nn dot ReLU. So either TensorFlow or pyTorch, both are providing this built-in function, these functionalities. Okay, so it will remove. See, who said this? You told that bias 0. You are not adding bias, but then why we use start dot 0 to initialize bias? Whenever we are considering, in few cases, you may not use bias. But whenever you are using bias, then you have to initialize. Okay, this is not all the cases. Sometimes if you want to add bias, you can add it. If you don't want to add bias, you no need to add. Okay, that bias 0. Okay, see what is bias? As I said, definitely bias must be there. So bias means you are giving the flexibility. Without bias, the learning curve always go through the origin. So how much shift we are expecting from the origin is the bias. So initially we don't know. So we are initializing with 0 or what are some value. Okay. Is bias? No. For every neuron, there will be only one bias, that is a scalar. That's it. Whereas every neuron, for this neuron, one bias. That you may represent as a vector. So, okay, so 2, 3, 4, B equal to, I will share the code so that you can understand, okay? Fine. Okay, so this is the case. Same thing, dot product, bias. Say neural network, ReLU is available. Here also same thing. So this is the way to declare a tensor. Here we are calling it a tensor. These are parameters. Parameters is also a tensor type. The tensor is inside, and that you are making it as a parameter. Okay, same thing, dot product plus bias, and then you have to add ReLU. Okay, so this is what we got. See, output always remains same in both the cases. Okay, next, 2 inputs. So single neuron. Okay, so 2 inputs corresponding this one. Okay, by inputs. So tensor dot product, same thing. It will compute the dot product between these two. Add the bias, then it apply the ReLU. Okay, so 2 inputs plus bias. Here 1 input. So 2 inputs. Same thing here also. See, here when you say, see, this is a dot product, x comma w, you are setting that x comma w. Okay, see here also, if you see, the formula remains same, torch dot x comma w, tensor dot x comma w. See, the size can vary, that is independent. This step will remain same. X you can keep on changing anything, like suppose 4.0. Okay, 3 inputs you are giving, and 0.7. That's it. It will run. Okay, so that is a efficiency here. You can increase the input, you can change the weight, but the formula remains same. What is the formula? Whatever may be the input, whatever may be the weight, we are performing the dot products. Okay, so see here, two inputs. Okay, same here, same like this. So I can add 4.0, and here also I can add 0.7. So irrespective of the size, same thing. Okay, so input, this is the parameter in the torch language, and this is bias. Now see, dot product you are computing between X and W, and you are adding the bias. That's what the Y value. Dot product, Y transpose into X plus bias. And then you are applying the ReLU functionality. Okay, so 6.4, 6. Okay, so like this, we are going to use the ReLU function. Okay, so next we are looking towards, okay, batch. Batch means it's more than one input. So till now we have studied one input. Okay, so like this, features, we changed the features. So if you see here, the input remains same, but the number of features we changed, one feature, two features, etc. But like this, if I have a batch, see here, batch, two inputs, one sample, then I have process another sample. Like this, we have n number of samples. Okay, so what is the shape here? 0, 1, that is 2, and we have 3 columns, that is 3. This is the sample 1, this is sample 2. Have you seen such batch cases earlier? In our demo, I have shown you. Can anyone tell me what is that? Can anyone tell me what is the batch? Now I have shown 2 samples. So where you have seen that? Yes, W comma X or X comma W, if shapes is same, it will work. Convolution filters, excellent, very good, Jihi Faridi. So when I apply first filter, so I am getting one activation map here. So this is the image, this is the image, this is the filter. So when I convolve the filter over this image, I got one activation map. If I have another filter, okay, again, if I convolve, I will get one more activation map, so that I can show it like this. If I have one more filter, I have one more activation map like this. As number of filters increases, my activation maps also increases. Okay, so this is the batch. This will go to the next layer. So this we call it as a batch. Okay, so here we have batch of 3. So here we have batch of 2. Okay, one sample, 2 sample. Okay, so here also 2 samples. Okay, so 2 samples we have, 2 samples, weight. So 2 samples means now input, what is the size of the input here? Input remains same. So this is 3 features. So what are those features for one sample? 1, 2, 3. Another sample is also ready. And what is that? That is equal to 4, 5, 6. Okay. So this is one batch is ready. Now neuron, this one, neural network. So neural network, okay. So neural network, you see how many neurons are there? 3 neurons. So I'm taking 3 neurons. Okay, 3 neurons. Then what will happen? So this is connected to this, this is connected to this, this is connected to this. Similarly, fully connected. Always we assume that every input goes to every neuron. So this is connected to this is connected to this. So total how many weights? 9 weights. So 3 into 3. So neuron 1 having these connected to each input. So first, what is the weight here? Tell me. What is the value of the weight there? What is the value of the weight here? And what is the value of the weight here? Tell me. So this is 0.1, 0.x. Very good, Juhi Faridi. Yes, Kirajan. Very good. Javed, yeah, good. Yes, Shikar. Yes, very good. So this is, and what about this? What about this? This line, this one? No, no, no. 0.2, yes. Yes, KS Arya, yes. 0.2. Okay, very good. So this is, see, this is the neuron, first neuron. Okay, this is second neuron, this is third neuron. Okay, so first neuron to first input is this. Okay, so first neuron to second input is this. This is the third input. This value is 0.3. Okay, fine. So now biases. See, always see, for each neuron there will be only one bias. Bias input is always 1, and we have to adjust the bias. So what is this value? 1.0. Similarly, this value, see, bias is always 1. The input is always 1, and bias, what is that value? 2.0, 3.0. That's it. Okay. Now see, this is the input 1 to 1, 2, 3, and what is the corresponding neuron 1? So neuron, these inputs, first neuron 1. So what are the neuron 1 weights? This one. So so I'm writing here for easy understanding. So 0.1, 0.2, 0.3 are the weights. Now that same thing, dot product. So 1.0 into 0.1 plus 2.0 into 0.2 plus 3.0 into 3.3. 3.0 into 0.3 plus bias. Bias is how much for this neuron 1. So this is the output. And this output, I'm applying ReLU. So ReLU, if it is positive, it will return same value. Next, neuron 2. Neuron 2 is having same set of weights from here, Next, the sample 2 comes, sample 2, this one. So what is the output for sample 1? 2.4, 5.2, 8.0. And what is the output for this sample? 4.2 for this one. So this is the output. What is the shape? 2 rows, 3 outputs. Okay. So this is the case where I'm processing a batch of 2 inputs. Each input is having 3 features, and I'm using 3 neurons. Okay. Now same thing we can use it here in the code also. So in the code also, see here, two inputs, 2 batch, and this is the neurons. Same, bias is a variable, weights are variables, and just see matrix multiplication. X into W transpose, X into W transpose. So at a time we are doing. So what is X? So see here, step by step we did, but here in the code, okay, we can do like this. Okay, so if you see here, okay, so this is the input. See, X is the input. So X contains like this. So 1, 2, 3. Next, 4, 5, 6. This is the input. Then weight transpose. Assume that if I don't transpose, so this is 2 cross 3. 2 cross 3 matrix. Okay, what is weight transpose? Here it's okay because 3, 3 matching. I will have one more example, I will tell. So now see, this is a weight matrix. So weight matrix is here. So what we are doing, I'm just see here, 0.1, 0.2, okay, 0.3. So what I'm doing, I'm transposing. So someone asked me in the morning, why I have to do transpose? Then what happens, see, if I do the transpose, it will become, it is 1, 2, 3. Then this is 1 input into weight. Say I have to do the dot product, right? Element-wise dot product. If it is like this, I cannot do. So if I transpose it, it will become like this. What will it will become 0.1, will become 0.2, it will become 0.3 transpose. Then I can do, say, matrix multiplication. It becomes a dot product. So 1 into 0.1 plus 2 into 0.2 plus 3 into 0.3. That will be one value. Next, same, because it already transposed another weight, this neuron weight. So this neuron weight will be here. This neuron weight will be here. Next, if I do with this, same here. So I will end up with 2 rows, 3 columns. Okay, 2 rows, 3 columns. And if you see here, the output, okay, see this bias also. After that, you can add bias, no problem. After once you get 2.3, shape won't change. Then you apply a ReLU, it will give you the output. And same is the case, parameter dot torch dot tensor, and then parameter dot, again, this is a tensor for bias. So X comma W dot transpose. See, W dot transpose here we are using. Here, see, you are using transpose of TF dot transpose. In case of TensorFlow, we have to use TF dot transpose of W. And in case of pyTorch, just W dot 3 plus B. then f dot ReLU. ReLU is available. What is your functional? So in functional, I have ReLU. So I applied. Okay. So if I apply 2.4, 5.28, 2.4, 5.28, both are same. Okay. Yes, if it is not matching, if it is not, if it is a condition, either you can use weight transpose into x plus b or x dot weight transpose. Okay. Now see, now another case, another condition. So this is how it will work. Now another case. What is that case? One input, 4 neurons. One input, 4 neurons. Weight shape is, see here, 4 neurons. Each neuron 3. So 4 neurons, 3 values. This is the input and bias. So bias is having some set of values. 4 neurons, one for one neuron, one bias. Okay. So now if you see, so let me explain why we have to see. Either you can use W dot transpose. So now I want, what I want to do, this is X. This is X and this is the matrix. Okay, so if I want to do dot product, if I do dot product, see, it will go wrong. If without transpose, this is 4 comma 3. This is 1 comma 3. This is 1 comma 3. This is 4 comma 3. This two should be same. Hence, what I want to do, either you do X dot W transpose, okay, or you do W transpose dot X, it doesn't matter. But the thing is, the shapes must be same. You must be able to proceed with the dot product. So shapes must be same. Got it? So because this is 1 cross 3, I am capturing the weights in the form of each neuron is having a weight. So 4 neurons, 3 weights, so 4 cross 3. This is 1 cross 3, mismatch. So what I'm doing, I'm transposing. So when I do transpose, what happened? It will become like this. So this will be, okay, this will be one matrix. Okay, now I can easily do the dot product. So that's why you have to transpose. Okay. So now I can transpose like this. Similarly, these two also. So this is the matrix. And now it became a 3 rows, 4 column matrix. Now easily I can do the dot product with X. Okay. So what I can do, I can put it here. Next, I can do the dot product. So this into this, this into this, this into this. And the output is 1 neuron output. And second neuron output. If I consider this, third neuron, if I do, fourth neuron, if I do. Then I can add bias and all. Okay, in these cases, definitely I have to go for transpose. So morning, someone asked me doubt. I think now it got clarified, right? So why you have to go for transpose? Because my input size must match with the matrix. So see, I am capturing number of neurons into features, but I need to multiply feature weight or input or feature into corresponding input or feature weight. Okay, that's why I need 3 input features. So 3 it has to be. Okay, is it clear? So I have to adjust. This is the weight. These are all the weights per neuron wise. So these are all the neurons. But how I am capturing the weights, if you see here, I am capturing neuron wise. I don't feature wise. So I will take one at a time. But in general, yeah, see, that you can do. But in general, input we keep as it is, only we play with the weight transpose. But internally, it's fine, no problem. Okay, so fine, that's it. So now you have to, so now same thing. So you have to take the dot product. You have to do the weight transpose into dot product x plus b. So that's what I'm doing here. 1 into 1 plus 2 into 2 plus 3 into this one. And then you apply the ReLU. So ReLU, you same thing, it will be same. Okay. So now check this here also in the code. So 4 inputs. Okay. Now see input TensorFlow. This is constant C. It is doing x dot transpose this plus B. If you run, you will get these values. Similarly here x dot W transpose plus B. Okay. So same values, same set of values, either in the TensorFlow, pyTorch. Okay. Weight transpose x comma weight transpose. So you can do this also. Okay. So you can do. Let me. No, it is not. It is mismatching. Weight transpose. Weight transpose. If I do. Uh, See, this is weight transpose. I'm multiplying with x. Okay, which is just dot product only, right? Okay, x. Okay, should not be like extra W transpose x. W transpose into x. Okay, okay, correct. Why? Because see, what is W transpose? W transpose means 3 cross 4. This is 4 cross 3. Double transpose means 3 cross 4 into this. So not possible. Okay, so it has to be like this only. X transpose W only. Then only the shapes will be clear. Like this shape has to be same. Okay, so that is the case. Next case, backpropagation. Okay, so till now we studied all the. I introduced everything like ReLU, input, output, okay, bias, ReLU, etc. Activation. Now, how it will learn the forward pass, loss computation, and backward pass. So I want to introduce completely. Okay, so now if you see backpropagation. So through backpropagation, I want to explain. Okay, so forward pass 1 input, 2 inputs, 3 inputs. Now you see here, I am representing the inputs as x1, x2, x3, weights as W3, bias. Okay, so I think how many of you know the forward pass, backward pass, etc.? Yes, yes, Juhi. So how many of you know forward pass, backward pass? So how model will learn? So first we will do the forward pass. Then see here. First we will do the forward pass. What is forward pass? By performing the input into x dot w plus b is the forward pass. And then we got the prediction. That prediction we will compare with the ground truth. The difference between the ground truth and the prediction value is called as loss. Then you have to compute the gradient, the contribution from each parameter. And then what we have to do is my new weight equal to my old weight W minus the learning rate into the gradient. So that is how you have to learn. Similarly, B plus equal to B minus the learning rate into dou L by dou B. This is how, then again, this W you use it for next set of computations. So until the weights, once your weights converge, the loss will converge. Okay. Let me take 1 minute, I'll come back. I will have some water and come back. Okay. So let me share the screen. Okay. Okay. So if you see here, this is how it will work. Okay. So we have to do the forward pass, and that is what this is the forward pass. We'll compute the prediction, then we'll apply the loss function, and we'll get the gradients. Okay. So see here. Now consider uh, there is a single neuron. This is the input, this is the weight, this is the bias, and the true predicted value is 6.0. Learning rate is this one. So what will happen in forward pass? The first W into X plus B, because shape is same. So you will do W dot X plus B. So 1.0 into 1 plus 2 into 0.2 plus 3 into 0.3 plus bias. You will add, you will get 2.4. This is the total value. Either if you can apply, if you apply ReLU also, it will be 2.4. Now you have to compute the loss. How you will compute the loss? Okay, loss equal to, okay, this one, mean square error. Okay, mean square error. So what mean square error will do? So 1/2 into the ground truth value minus predicted value whole square. Okay. So now if you see 1/2 means 0.5, what is 6.0? Ground truth value. So ground truth value, how much your model predicted? It is 2.4 whole square. If you compute this, we got 6.48. So 6.48 is the loss. And now what we have to do is we have to compute the gradient. That means with respect to the variables. Okay, dou W, dou V. Okay, now see dou L by dou W. Okay, so loss function equal to, so you know, right? So loss equal to 1/2 into this ground truth minus, okay, weight into X plus B whole square. Okay, next dou L by dou W equal to 1/2 into 2 into this particular value, that is y minus this value as it is will be there. So I'm giving it as a y cap into, okay, this one with respect to W. If I do that, I will get minus X. Next, this will cancel. Okay, it will be like this. Next, dou L by dou Y equal to same thing. This will be there. Okay, Y minus Y cap into, if I differentiate this, okay, if I differentiate this, I will get 1 because Y product is 1 dot Y, so I will get 1. So dou L by dou B equal to Y minus, okay, this one, okay, Y minus Y cap. Clear? Dou L by dou W, sorry, not Y, B, dou L by, see, Y minus Y cap is dou L by dou Y. This is dou L by dou W. Next, I need to perform dou L by dou B. Then also same thing. So Y minus Y cap remains same into, next, here I have to do. So this will be Y minus WX minus B. So the differentiation with respect to B means into -1, okay, which is equal to minus of Y cap minus Y. So what is Y cap? Y cap equal to 2.4. So 2.4 and this is 6, okay, which is equal to 3.6 minus 3.6. Okay, this is the value. Okay, and now you will apply next same parameter update. So how you will update the parameters? I given the formula. What is the formula you are going to use? Okay, as I said, the old equal to new equal to old minus learning rate into dou L by dou W for weight. Same thing, dou L by dou B for the bias, because these are the two parameters which we have to learn. Okay, that's it. Okay, dou L by dou W. Now, same thing we are going to check with the we are going to check here. Okay. So see here, torch. So I'm taking X as an one input. Y is the 5.0, only one input. Okay. So this is the weight and bias. So what is optimizer? Optimizer is stochastic. See, backward propagation. So what happens in the backward propagation is, if you see here, see, this is the input. This is the input, okay? So backward propagation, there is a formula. Because I don't know the W and I don't know the V, I will select random values. But these random values, when we say that W comma B is correct, when my loss is approximately equal to 0. If my loss is non-zero, these are not optimal. So I keep on repeating, I keep on updating the weights. So how I will update the weights? Okay, first initially I will start with some any random value because these two I need to compute. So W equal to 0, bias equal to 0. So how I will update? I will get new value. Just I'm using plus the next value equal to my current value minus the learning rate into loss with respect to the loss function. So dou L by dou W and B plus equal to B minus neta into gradient with respect to B. So W I know, learning rate is a constant I can set up. So I just need to compute dou L by dou W and dou L by dou B. For that, I have to express differentiation. This goes to differentiation. I have to express W in terms of L. How I can express? L is a mean square error, which is equal to 1 by 2 into Y minus Y cap, the difference between the ground truth and predicted value whole square, which is equal to 1 by 2 into Y is the ground truth value minus, when I will get my predicted value, I will get my predicted value when I do this weight dot transpose into X plus B whole square. So this is the loss function. So now here I can compute two things. One is dou L with respect to dou W, because I can able to frame how much W is going to impact W, and dou L by dou B, because B is also there. So when I'm differentiating with respect to W, I'm treating this as a 1 by 2 X square. What is differentiation formula? 1 by 2 into X square, 2X, 2 into X. And again, I have to differentiate X dx. Correct? So same thing here. So dou L by dou W equal to 1 by 2 into 2 into X. What is X? This entire thing. So I'm calling for a W minus, I'm calling this as a Y cap. But now I have to differentiate this entire function, second, this dx. But I'm doing with W only. So this is constant, this is constant. Okay. So when I do with this W, okay, then what happens? It will become minus X. Why? Because W into X, I'm partial differentiating with respect to W, it is X, and this minus will be there. Same thing here also with respect to bias. So this will get cancelled. So Y minus Y cap into minus X. Here also same thing. Y minus Y cap into the B. I have to differentiate with respect to B. So Y minus Yx minus B. So I'm differentiating with respect to B. This will others will be constant. So minus B differentiation minus 1. So these are the two values which I'm going to substitute in dou L by dou B, dou L by dou W. Repeatedly, and keep on computing, and then I will get my W plus converts to, I will get some values. These values I will use to compute the Y cap. And then I will compute Y minus Y cap. So my loss will converge to 0. Is it clear? Is it clear, Binny? See, Abdul, why you are asking this question? Why do we apply scaling to values in data set? Did we discuss that? Why you are bringing in this concept? We are different. We are learning partial differentiation. We are learning something different. Then why you are changing the topic? What I have discussed, what I am discussing, please restrict yourself to those only. Why do we apply scaling? Means again I have to apply scaling, which is not the topic here. Okay, so don't ask unrelated to current topic. Okay, so Binny and Juhi, I hope you understood. Okay, so that's how you have to start in calculus. You have to choose some random values and you keep on iterating the formula, this formula, and somehow you will get say 0.6. 0.8, something like this. That if you substitute in YCAP, that results into closer value to Y. Then your loss will become 0. Such W and B you have to compute through partial differentiation. Okay. So hope, so now same thing. Okay. What I explained, stochastic gradient descent. So I want to compute between W and B. My learning rate is 0.01. So this is neta. Where is neta here? This one. This one is what? 0.01. We have to set it. Okay. So that is hyperparameter. So I said 0.01. We are applying stochastic gradient descent. The formula which I explained, simply I can do SGD. Okay. So by simply setting SGD, see torch dot optimization. So I am finding the optimal W and optimal B. So inside the torch, in the optimization, we got SGD values. And what I'm optimizing, I am optimizing W comma B. Okay. See here. So that is X and Y set, and initially I'm setting weight as 0.5 and my bias as 1.0. You can set any value. Okay. And then see optimizer.0 grad, clear any previous gradients. Now the forward pass, I'm doing the forward pass, which is equal to input into weight plus bias. And you can apply the ReLU also, no problem. Loss equal to 1/2 into the ground truth minus predicted, or this one, any whole square. And then simply I'm using loss dot backward. So here I'm computing this entire steps which I explained. That is what we are computing here in the backward. Once you compute, see, this is the computation. This is computing the gradient. Dou L by dou W, dou L by dou B is what we are computing in case of the loss dot backward. And once you compute, you have to update. What is the update step? This is the update step. You are updating to new values. This will happen in this step. Like this, you can keep any epochs. You can keep on doing. Okay. So when you run that, so predicted is 2, loss is this much, and next set of weights. See, initially I started okay, 0.5, 1, and this is the gradient. And then you can apply the next values. Now tell me what is now with this, tell me the next set of weights. With this, can you tell me the next set of weights? So you got this. What's the next set of weights? Yes. Yes, gradients we no need to compute, but what it will compute is like this. Okay, so you have to understand what happens inside the keyword. So when you say loss dot backward, this is what happening inside. We no need to compute. Yes. Now tell me the values. Next W set. So initially I started with the values. What are the values? Weight 0.5, 1.0. By using this, I got these values. Now tell me the next round, what will be my W and B? Very good. So let me check. So is that correct? So why difference? So same thing. So I need to compute my word value, which is equal to my weight. So what is the weight here? My weight initial value is 0.5. So, okay, so it is equal to 0.5 minus the neta. The neta is the learning rate. Okay, so the learning rate is 0.01. So learning rate is 0.01 into the gradient value. So what is the gradient they given? The gradient they given with respect to W is minus 6.0. So minus 6.0 you have to substitute, which is equal to 0.5 minus into minus plus, okay, 6 by 100. That it will become 0. When you multiply 0.06, which is equal to 0.5, 0.506. So we moved from 0.50, 0.56, sorry, 0.56, something like this. So a simple improvement. So 0.5, 0.56. This is the next set of value which I will use it for updation. Next, again, loss I will compute. Until my loss is not equal to or some threshold, I will set my loss must be 0.0001 until you keep on updating W. I can set like that and I can proceed. Okay. Yeah, that is the case. Okay. Now, if I will do the same thing here, same thing, but when I do with TensorFlow, say I'm taking the same set of inputs. This is my predicted value. These are my weights initialized. Okay. So I need to go up. Oh. Okay, for this, I think I have only this one. No issues. No issues. So see here, same I'm explaining here, TensorFlow and this one. Okay, so these are the inputs. 1, 2, 3. This is the output. I initialized my weights and biases. So number of inputs, bias, learning rate. So I'm using gradient tape. So here I'm computing the gradients. So these gradients, the gradients which I computed. So by using TensorFlow.gradient tape as tape, it's like a recorder. So I'm using the forward pass. So forward pass is dot product between input weight plus bias, and then I'm computing the loss. So once I compute the loss, I need to, once the loss is computed, then what I'm doing, those values are available to me, loss and W comma B, if I pass, I'm getting the gradients. Once I get the gradients, I'm applying the formula. Same thing. Okay, loss with respect to this one and dou L by dou W, weight, update weights and biases. Because I have three weights, I need to compute dou L by dou W1, dou L by dou W2, dou L by dou W3, dou L by dou B. That is how the number of parameters, the number of, as my number of features increases, my number of weights increases. As my number of weights increases, my computation increases. Okay. So any doubts still here? Same thing. I just, okay. Any doubts? Okay, if I want to same with the torch, 1.0, 2.0, 3.0 is the input. This is the output. And weights is a parameter, 0.1, 0.0.3. This is the torch. This is the bias. So learning rate. See dot product, forward pass. See simple. A dot product between input and weights plus bias. And once you get the prediction, I can compute the loss function. See, when I can say loss dot backward. So when I say loss dot backward, automatically, so see here, loss dot backward, we are computing the gradients. Gradients are available. And once the gradients are available, I can update my weights. Okay. During the backward pass, the gradients are computed. The gradients means this one. Dou L by dou W1, dou L by dou W2, all those are gradients. Okay. Once I know the gradients, next I can update the values. Okay. So these are the values. Same. Okay. Predicted 2.4. Here also predicted 2.4. What is the loss? 6.4. Here also loss 6.4. Dou L by dou W minus 3.6. Minus 3 point. Same. Everything remains same. Everything remains same. Either you use pyTorch. This is a TensorFlow. Same thing. But the way you first you have to compute the loss. Once you compute the loss, then you can apply the gradients. Tape dot gradients. Okay. So tape dot gradients. Here, no grad. This is how you compute the gradients. Okay. So you just have to know how to do the this one. So here we are doing the forward pass, loss computation, backward pass. And here how we are in the torch, or how we are doing forward pass. So you have to compute like this, forward pass and loss computation. So no need to assign random weights randomly. So here there are some, see he underscore uniform. Okay. In Keras, we have weight initializers. We have concept called weight initializers. So layer weight initializers, you can use those. See here, like this, you can initialize kernel initializer. Okay, it can be random normal initializer, or it can be random normal. Okay, random uniform. Next truncated normal. Okay, next like this gloret normal. Okay, like this we have various initializers which will work for you, that we can choose. So wgrad we are not have defined that is coming from backward. So we need to check that last backward will return from the document. See, this is w dot this gradients, w dot grad and this one. These are the gradients. So which we require for the computation. That is what it is computing. In the backward, the gradients are computed. Once I computed, I'm updating those weights. Okay. So in both the cases, it will remain same. Clear till now? Any doubts? Any doubts till here? Anyone? Pooja, Dhanlakshmi, Gopinathan, Kaushik? All clear, very good. So which concept you learnt and which earlier you felt very tough, now it got clear? Which concept it got clear now, today, after our discussion? Like gradient, very good. Forward pass and backward propagation. Minimizing the loss became clear. Because, Abdul, we have to keep on repeating, like until a loss to our satisfactory level. Okay, so we may not get zero. We never frame a function which is closed, which can mimic the dependency between the input and the predicted value, but minimal level. Okay, so now next go further step. Let's see. I slowly increment towards further level. Okay. Okay. So now this is over. Okay. Now single layer neuron with 5 neurons. Okay. Now 5 neurons. How I am going to deal with 5 neurons? It doesn't matter. See, 1, 2, 3, 4, 5. Now tell me, if I want to deal with 5 neurons, what are the things will change here? See, backward, any predefined function. No, this is how you're computing the backwards. See here, last dot backward. So see backward, automatically when you say last dot backward, automatically see you are using w dot grad. But w dot grad you didn't compute it earlier. When you do last dot backward, automatically these are computed. Okay, fine. Now tell me, if I use 5 neurons, what are the changes? Which are all the parameters? Which are all the matrices will change? Weight matrix, bias matrix. Okay, that's it. That's it. Input weight, yes, inputs also accordingly. Okay, but input, okay, we cannot say, but in this case, input also got changed. Okay, now see what will happen. So 5 neurons input, I have 3. That means I have 3 features. Okay, a vector or array with 3 features. Okay, and I have 5 neurons. Okay, next bias, because bias is also 5, because 5 neurons, 5 biases, 5 output. Okay, and now what we need to do here? Okay, that's it. Okay, so now let's go to the code. Okay, I did more explain to code here itself. Okay, so this is the case. This is what we studied, right? Now see, this is TensorFlow. Same we got. Now see, torch gradient. Fine, 5 neurons per layer. Now see here. So input is 3, 5 neurons. So each neuron is giving the output. Okay, so each neuron is giving the output. Okay, next learning rate. Now see, I kept in a epoch. So I kept 10 epochs we are doing. So what we are doing, forward pass equal to weight into x plus b. So see here. Now matrices, matrix and vector. Now weight becomes a weight matrix. This is a vector input. So matrix into vector plus b, linear algebra. So whatever operations we can perform with uh, we need for linear algebra, everything is predefined. One such function is matrix vector. Matrix is a weight, vector is a input. Plus bias. We got the prediction. That's it. Matrix into vector. What's the matrix? Matrix is a weight vector. What is the input? Input is this. So input is this. And what is the input shape? 1 into 3. And what is this shape? 5 neurons. And each for each input, okay, for each input into 3. Okay, so obviously shape mismatch. What you have to do? X into weight transpose. So here you have to do the weight transpose. So 3 into 5. So now what I will do? So now 5 neurons are there, right? So this is my input 1 cross 3. This is my input 1 cross 3. 3 cross 5. Okay, so 3 rows, 5 columns. This is for neuron 1. So input into this one will get an output for neuron 1. This into this, I will get output for neuron 2. That's why we have to use weight transpose. If weights are mismatched, I have to go for transpose to make the computation feasible. Okay. So if you see here, linear algebra, this is done. That's it. And then what I am doing, see here. Okay, because 5 square differences. Now what happened? From this is an output, this is an output, this is an output, this is an output. So I have y cap. So y cap, 5 values now. 5 values. Each for my y cap is not a single value. No, my y cap is a vector minus, okay, my predicted values. My y is also a vector. So 1 by 2 into whole square. 2 vector, difference between 2 vectors whole square. That is what C, 0.5 into TF dot square, y predicted minus y true. I am taking the average, mean of 5 square differences. Okay, I'm taking the average. Okay, mean or you can add whatever it may be. So here what is happening, the difference. Okay, so difference between this and this. So 1 by 2 into first neuron predicted value minus first neuron ground truth whole square plus 1 by 2 into second neuron. And like that, you will add and divided by n number of neurons. That will be my loss function. Okay. So that is how I compute the loss function, and I keep on doing that. And then once I compute the loss, I'm applying TF dot gradient. So apply the gradient with this loss function. You compute the gradient with respect to W and B. So I got dW dB. Once I get dW dB, I'm applying this. Apply gradient descent. Update this. I'm printing. Then again, I'm going back. Next, with this new value, I'm computing. Then again, okay. So I can do it 10 epochs. So this loss, my loss is converging. So let do it for 1,000 times. See here, my loss is reduced. Okay. See, my loss became 0. So when it became 0, almost. So if I loop through some almost for 100 itself, I think see, loss function became 0 here. Here. So 205 50 epoch itself, I got 0. That weight is the optimal weights, which we don't know. So 205 epochs, 5 times I need to keep on updating it. Okay, that's why. Okay, that's how it depends. Okay, randomly I'm choosing. Okay, clear? This code, same thing here also. In PyTorch also we are doing the same thing. This is the PyTorch, same thing. Neurons, predictions, randomly choosing 0, 10 times I'm doing the same thing. Now tell me, can we expect the same here also? Can we expect the same? See here, see almost here it didn't approach 0. See, 205, still some loss is there. Okay. See, any number of neurons. I just taken because I'm explaining only through 1, 2 neurons. This time I have taken 5 neurons. You can take 20 neurons. Okay, it all depends upon how we design the network. Yes, see, we are not minimizing the loss function. We are updating the weights and biases. That itself updating the loss function. So, okay, got it? So loss function is getting minimized through updating weights and biases. We cannot stop. First time we have to run. So next time, see, suppose here, so here if you see 1000 epochs, now I come to know from TensorFlow that 1000 epochs are not required. 205 itself, it became 0. So I am just keeping for 210 epochs. So we cannot stop it. Okay, so done. The other 1000, we make it this one. Okay, so this is how we can do it with PyTorch, and this is how we do with the TensorFlow. Till here, any doubts? Clear? Everyone, any doubts or clear? Yes, loss is because of my difference in the predicted value. Predicted value comes from the weights and biases. That's why you have to minimize weights and bias. Yes, you can initialize. You can initialize. Okay, see here. Here also. In PyTorch also. See, random. Okay. So we can initialize. Okay. So see initialized weight. How to initialize weights in PyTorch? Okay. So let me check single layer. See, here also we have Xavier uniform. Okay. And see like this Xavier uniform. Yes, same. Whatever available in TensorFlow, here also it is available. Data dot uniform. Weight dot data uniform. So uniform distribution, it will take the weights. Okay. Got it? Can I? Sorry, Juhi. Conditional statement to stop. See, why you have to, yes, we have to search. See, why you have to apply conditional search? Just like first time you run it, next time you reduce the number of epochs. Okay, so no doubts, then go further. Same thing here. Now, what we are doing is, see, I have taken two layers neural network with batch input. Two layers. Okay, two layers means like this. Okay, so this is the layer, another layer, two layers. Let it be any number of neurons, no problem. Okay, the input to this neuron layer is this. Input to this is this. I will feed in. And what is the input to this layer? What is the input? output of the first layer. Very good. So the output of this neuron, output of this neuron, output of this neuron. So this neuron output will go to all the layers. This all the layers. This output is also goes to the all layers, and then we will get the output. Same thing. So you have to write it like that. Okay. So if you see here, so X is the input. We have two inputs each of 2, 3, and these are the predictions. Okay. This prediction, what it says that what is how many neurons are there? What is the output? What is the number of neurons? How many output? How many neurons are there in the second layer? How many neurons are there by looking into that code? Can you say how many neurons are there in the first layer and how many neurons are there in the second layer? Okay, very good. Gautam. Yes, Gautam Kumar is correct. So what is the number of neurons in first layer? How many neurons in the second layer? Yes, we assume that it is fully connected. Yes, so Juhi Faridi. Yes, it is 5, 2, not 1, Gautam. It is 2. 2. Okay. Yes, correct, Dhanlakshmi. Fine. So same. Now everyone, you got it. So I have an input, 2 samples. One is sample 1, sample 2, and a sample. Yes, bias is also there. From this also you can see. This also you can see to say the output. Not only the bias. This is all the clue. Okay, fine. So this is the input. So how the network will look like? Let me draw. So I have an input sample. So from this, okay. So from this, okay. So this is my first input. So this is my first input. Okay. So input, but I don't know. But what I did is I have 2 neuron layers. This is one layer. This is one layer. As of now, I don't have any clue. And see, this is another weighting sample. Okay. So after first input is over, I'm using this one. But I don't know. But see, here, this is the output layer. This is the output layer. Output layer is telling 2. Okay. So output layer is telling 2. One neuron will always give one output. So if you want to get 2 outputs, you always need to have 2 neurons. So one neuron, another neuron. That's how I fix it here. Next, what about this one? I can have any number of neurons. So if I see here, okay, so if I see the weight initialization is telling that 5, and bias is also 5. So anything it will be a clue to us. So obviously I have 5 neurons. So this is 3, this is 4, this is 5, this is layer 1, this is layer 2. Each input, okay, each input will be like this. Okay, so it will be like this. And then this we will feed it to everyone. Okay, sorry. Similarly, this we will feed it to everyone. And the output is 5. Same thing. This I will feed it to every network. This is the output. So this is the network structure. Now tell me how many weights are there? How many weights here? So how many weights here? And how many weights here? So red, how many weights? Yes, input into number of neurons, 3 into 5, 15. Here, how many? Here between L2. Yes, very good. L2, layer 2 here. 10, 5 into 10. So total 25. Next, how many biases? Very good. 5 into 2. So 5 into 2, 10. So total parameters, how we can compute is 35. So number of parameters. When I say parameters computation equal to number of weights plus number of biases. How you will compute the number of weights equal to, okay, input into number of input features into number of neurons in layer 1 plus, okay, next number of neurons in layer 1 into number of neurons in layer 2. Like this, how many neurons I have, those many computations I have to do. And then what about the number of biases, which is equal to number of neurons in first layer into number of neurons into second layer, like that, product of the number of neurons at each layer. So this is how you are going to compute the weights and biases. If you add them, that's what we are calling it as a parameters. And the aim of the any learning is learning these parameters. So input is fixed. Okay, so if you see here, my input is fixed in the code. My code input is fixed. My output is fixed. The only thing I need to learn is the network and which maps input to output. That mapping is done through weights. So I have to learn the parameters. That is called learning. When we say that we are doing machine learning or any learning, what we are doing is, okay, so what we are, okay, so number of parameters, number of equal to weights into biases. Learning those weights and biases is called as machine learning. Okay. How are number of biases equal to 10 means in first neuron, it, oh, very good, very good, very good. Who is she? Very good. I just missed out the thing. Yes, you see, we no need to multiply here. Here we have to add. Here we have to add. Why we have to multiply? Sorry. Number of neurons at each layer we have to add. Okay, so if I say N1 neurons at first layer plus N2 neurons in the second layer plus N3 neurons in the second layer, which is equal to the bias count. Okay, but when it comes to weights, you have to add input into number of neurons plus number of neurons in first layer into number of neurons into second layer. Like that, it will continue. This is equal to weights. That is equal to bias. Okay, very good. Fine. So see here now, that's how you have to adjust. So weight 1, that means this is what we are calling, it as a weight 1. This is what we are calling it as a weight 2. What is weight 2? Weight 1 matrix. I have to compute a matrix. How many, what is the number of elements here? For each, number of neurons. For each neuron, okay, 5 neurons are there. And 5 features are there, input. Okay, I1, I2, I3. Okay, so number of elements I have to learn equal to inputs into number of neurons. That is what we are doing here. So random 3, 5, where 3 is the number of features, 5 is the number of neurons automatically. Okay, next bias, first 5 neurons, 5. Same here. So here I will have 5 into 2, so 5, 2. So 5, 2, biases 2. So that's it. These are the weights I have to learn. Learning parameter is there. So I am doing through epochs. First one, forward pass, input into weight plus bias. I am applying the ReLU activation. I got A1. Okay. Next layer, this output from A1 into the weights at W2 initially. So initially W2 is a random vector plus B2. That is what Z2. So Z2 is what my prediction. By using prediction, I am computing the loss. Loss, I am backpropagating. When I say backward, I am computing the gradients. So there are 4 types of gradients, W1, okay, W1, W2, B1, B2. So I computed the gradients. This is a vector because this is a matrix, okay, and that's it. I'm zeroing. Then like this, it is keep on continuing, okay. So loss is converging for 10 epochs. Let me make 100 epochs. 100 epochs, is it converging? And no, it's not converging. So let me make it 300, okay. Okay, that's it. It's not converging, so it's stopped here. Same. So is it clear? Any doubts in the pyTorch? Same here also. the input, and this is the output. So here we are using tf.random.normal 3, 5. Okay, and bias equal to 5. Okay, 3, 5. And if it is 2 here, actually this is 2. 2. And how many biases are there? 2. Okay, so that's it. So I think this is 3-layer neuron, 3-layer neural network with, sorry, this is 3-layer, this is different case. Okay. Okay, so this is different case. So this is how it will work with pyTorch and TensorFlow. Okay, this is with TensorFlow. Okay, 2-layer neural network with 5, this one. Is it clear? Yes, bias is equal to total number of neurons. Yes. Any doubts? See, syntax, you no need to remember. You no need to remember the syntax. I also don't know the syntax, but what to do? Forward pass, last computation, compute the gradients. That means backward. Then computing the gradient. So that is how you have to learn. Okay. So backward, I got the gradients. Now next I have to update the gradients. See, forward pass is very simple. Input into this one. Forward pass is this one like this. Forward pass is this one. Forward pass is this. Okay. So this is the forward pass. Input into weight plus bias. So each neuron will take an input. It is having corresponding weight. So input into weight. So input into weight plus input into weight plus input into weight. Like that, all the neurons. Input into all the neurons, you will get the output. Okay, so that is done. Now let's go to somewhat more complex. So what is more complex? See here, 3-layer neural network. 3 layers. Okay, so 3 layers means one more layer added. One more layer added together. So if one more layer added together, okay, same thing. That is, you have to adjust like this. So see here, TensorFlow, 3-layer neural network. So I have batch of inputs. Next, Y, 2 outputs. So these 2 outputs is that my output is 2. 2 neurons are there. Next, W1, B1. That means this one. W1, B1, W2, B2. Here also, because of 3rd layer, I will get W3. That's it. I have to initialize here. I have to initialize. So W1 between 3 inputs, 3 features, and 5 neurons. What is B1? Number of neurons. Next, W2. TF dot variable. This 5 is the input, and 4 is the number of neurons in the 2nd layer. 4 is the number of biases. Next, 4, 2. This is the structure. So here I have 5. Here I have 5. Here I have 4. Here I have 2. So that is how you have 5 output, that is forms as input here. 4 is output, that forms as input here. Okay. So I will take 3 features, 5 is the first weight. Because of this 5 neurons, bias is also 5. Next, this output forms as input here, 5, 4 neurons are there, which will give an output 4. And number of biases is also 4. Next, this 4 form as an input to my output layer, which is having 2. Okay, so 2 is the biases. So 15 plus 20 plus 8. Okay, 35, 43. So 43 weights, 5, 4, 9, 10, 11. Okay, so 54 are the total number of parameters. Okay, so that's it. Everything remains same. A learning rate, so I'm looping through 10. So I'm using gradient tape, match multiplication between input weight plus bias, and then I'm applying the ReLU nonlinearity. That A1 is formed as an input to next layer, weights are W2, which is initialized here randomly, plus bias. Next, I'm applying ReLU. That Z2, if I apply ReLU, it is A2. A2, I'm applying with W3, that is Z3. So that output equal to my predictions. And by using that prediction, I'm computing the loss function. Once I compute the loss function, by using this loss function, I have to compute the gradients for W1, W2, W3, B1, B2, B3. That's all we are calling it as a this one. By using that, I'm updating my weights. Then again, I'm entering into the loop. Okay, so this for loop is still here. Next, again I will go back. I will use second time, I will use new weights. Okay, so last part here, same thing. Same will work here also. 3, 5, 5 bias, 5, 4, 4 bias, 4, 2, 2 bias. Next, epoch 10 epochs, input into weight plus bias. That is what going to ReLU. That is called activation. That activation I'm using into weight transpose plus bias. Okay, Jet2 I am applying ReLU. I got A2 form as input here into weight plus bias. Same, I'm computing the mean, then backward. I'm using backward. Because of this last function, these gradients I'm computing. All these gradients I'm computing here. And that's it, I'm applying the formula. Next, I'm clearing the gradients. Okay, reset the gradients to 0. Next, I'm looping. Okay, so see here, after 10 epochs, my loss is 3.50 in case of pyTorch. In case of TensorFlow, it is 3.19. Okay, but anyhow, let's see how it will converge to maybe after 100 epochs, how TensorFlow is performing. Okay, so when it becomes 0, okay, 1.6. Okay, so if I do 100 epochs in case of pyTorch, what will happen? So in case of pyTorch, 0.02 loss. Okay, here 1.6. So pyTorch somewhat converging better, but we cannot generalize. In this case, it is working. Okay, so any doubts? In TensorFlow, we will define DWD gradients, while in pyTorch, we get automatically. See, here are we, in both the cases, we are getting automatically, Jihi. So here also, so in TensorFlow also, see here, it is computing. So you are just storing, that's it. This is how you are, the output of this step is for loss, I'm computing gradient with respect to W1, loss with respect to V1. Those values I'm storing here. Okay, I have to store. Here, what is happening? The name automatically in this variables it is storing, so I'm using that. Not much difference. Why was the output for TensorFlow different for same number of? Oh, see, it all depends upon the random. See, here you have to think. Pooja, who asked this, Pooja, you have to think why it happened. See, because I'm using random. So these random n weights are, I'm not using same weights. I'm using random. So here also I use a random. So weights are different. Okay, see, I'm using random.normal. Okay, here I'm using rand. So whenever I'm using rand, it's not in my control. So I'm using different set of weights. So obviously it will impact the convergence. Okay, so any doubts? Hope it cleared, right? Any doubts? More or less same. Yes. If you use everything same, it won't have much impact. See, like suppose 5.1, it may be 5.13 or 4.9, very minute difference, but not drastic like 5.13, 5.12, no. Not seed. Here, seed is not the problem. Okay, if I use seed, then it may generate same random numbers. Yes. Because the random generation depends upon the seed. So, yes, you can try that. Okay. So, in the last case, same thing we discussed, but now I want to give an example of a classification problem. So, classification, same thing. I take an MNIST. So, see here, data sets, three different data sets are available in TensorFlow. So, MNIST.load. I do it. So, I got train and label, test and label. I'm normalizing the data. This is what Abdul asked the question. So, why we have to standardize? So, why we have to standardize means, see, if a few variables, suppose population. So population always in terms of crores. Okay, so 2 crores 35 lakhs, 7 crores 65 lakhs. And if you take age, so average age of suppose India population 2 crores. What is the average age? Average age may be 30 years. US 7 crores population, average age. Okay, average age may be 36. Now, if you see, when you take these two features, this features is in terms of crores. This feature is in terms of tens. So If you see input into weight, so what you are doing, the entire learning is input into weight. Okay, so here if you see input 2 crores into weight plus 30 into this, so this feature will get dominate. Learning from this feature won't be there. So this higher number, back forward propagation, input into weight, if input is higher, that feature will dominate. That's why model may focus more on this, it may ignore this. That's why you have to make every value between 0 to 1. Then it will be equal importance. That's why we are standardizing. Okay. Yes, Pooja. Okay, fine. So that is normalizing. I'm reshaping. So I want a fourth layer. One hot encoding I'm using. Okay. Same here. Variables. Input. What is the weight? So 784 is my input. Why? Why? Because 28, 28 is my input size. So 784, 128. So I'm using 128 layers. Okay. Next bias 128, 128. Next output is 10 layers because 10 class problem. So 10, my bias is 10. Same thing here. I'm epoching. Okay. I'm taking the batch and I'm using the forward pass, ReLU, and same, I'm passing through this one, computing the loss. Same I'm doing here. Okay. So if I do that, same, see classification problem, I just made, see here, Y test is there, Y test is there. In case of classification problem, the thing is we have 10 class problem. That's it. No. Class imbalance, feature normalization is nowhere related to feature imbalance. Even though you have equal number of samples per class, but also you have to do. Why? Because some features are having higher values, some feature having lower values, make the model confused. It may focus on the feature which is having the higher values. That's why you have to normalize. Okay, so it is same PyTorch also. You have to declare, there is a built-in feature, there is a built-in data sets available. So transform, MNIST, see, data sets are available. I got MNIST data set. From MNIST, I got the trained and test data set. So I initialized same 78, 128. Those are the random numbers. I just multiplied with 0.01, or you can just delete it, no problem. Same structure, see, same here, 784, 128, 128, 10. 784, 128, 128, 10 biases and learning rate epochs, this one. And see, train loader, batch, I got one hot. So batch into weight plus bias, ReLU, that forms as input to next layer, weights plus bias, predictions. Okay. And that predictions, I'm taking the loss and backward, same steps. Okay. So if I do this, I got this loss function. And this is the TensorFlow. This is the loss. So PyTorch, what happened? Loss started very low and converged. Okay. And TensorFlow, loss started at very high and taken time to converge. This is for classification, full problem, full network. Okay. Yes, any activation. It doesn't depend upon activation. For any activation, this normalization remains same. Okay. So any doubts in the classification problem till now, from the morning to till now? Any doubts? Keras is used for no. Here Keras and see here this TensorFlow is a wrapper. So inside Keras, on top of it we have TF. Okay, so that's it, wrapper. So it's very complex. So TF makes easier. That's it. See what one hot encoding will do is, suppose I have a cat, dog, elephant. Okay. So one hot encoding means, see here. Suppose if the label is dog, then I will make it as cat 0, dog 1, elephant 0. Okay. That is called one hot encoding. Which feature the sample is representing, I will convert like this. Rather giving the values, okay, 0, then 1, 2 like this, what happens? Initial, suppose if one sample is there, that is cat, another sample dog, another sample elephant. Now, if you see, the number is increasing, so higher value that may dominate. So what I want only two values. I want to represent the feature. See, batch size. What is a batch size and epochs? See, what is batch size? I have 100 samples. I have 100 samples. 100 samples I cannot at a time I cannot move it to my machine and run. So what I will do, I will make it as a batch. Batch means subset of samples. I will take this batch. I will give it to my model. Model will give the output. I will get the predictions. I will compute the loss. Then I will backpropagate. Then I will take another batch. And then that batch I will feed as input to this model. I will get the output, compute the loss, backpropagate. Next, like this. So entire input I may not able to store in my machine. So I will take batch by batch and I will process. If I go through the entire data set, that is called as one FO. Then again I will go back. Then again I will glance. Again I will glance. So like this multiple times I will go through the entire data set with batch by batch. That makes me to focus on all the important features. Okay. I need to check the data set, Juhi. So if you send me the data set, then I can check how encoding we have to do in this case. Okay, but ultimately we have to pass only numeric. It doesn't understand any non-numeric cases. Okay, so any doubts? See, big batch size means see, it's nothing like that. Depending upon, see, if we generally you can take entire batch also, but sometimes memory doesn't suffice to process. That's why we will take batch by batch. If my image is 512 into 512, I can process 50 at a time. I cannot process 1,000 at a time. So that is the flexibility. Yes, yes. This is memory convenient. That's it. Okay. So any doubts? If anything, we have to hit and trial. Start with 2 batch, 4 batch, 8 batch, 16 batch. Like that, you have to trial and experiment. See, always you have to give all features at a time. So one feature at a time, then how we will train another feature? So you have to do all features at a time. And if the features are more, you have to do dimensionality reduction, reduce the number of features and feed it to the model. But at a time, you have to give all the features. You should not cut the features. Means, sure, sure. Okay, so any doubts? 2 minutes left. So any doubts? Else we can close. So this is my email ID. So please share your feedback. So how is the session? Is that fine? Are you able to understand? Clarify your doubts? Yes, everything I will share. No issues. Everything I will share. I'm not getting the Kaushik. I'm not getting what you are asking. See, you don't confuse, don't make things complex. Either you do TensorFlow or PyTorch. Okay. So you don't merge. Okay. It will throw some errors. You can use, you can run, no problem, but unnecessary issues. Which website? See, lot of just lot of bidders are there. Okay. No specific. Yes, Kaushik. I pinged in. Okay, so let me give my email ID. Okay, that is my ID. Yes, we are selecting a batch because if my memory size is very less, I cannot accommodate entire data set into my memory. So what I need to do is I'm splitting that and I'm processing one batch at a time because entire data set I cannot process due to my memory constraints. Trial and error, Juhi, trial and error. Okay. So few parameters, see, one or two parameters you can set, okay? Others you can make it default. If you're not getting the correct output accuracy, then you try to explore one by one. Okay. Yes, everything I will share. Everything I will share, no issues.
Okay, shall we conclude, sir?
Yeah, sure. Okay, thank you. Thanks all. Thank
Okay,
you.
thank you so much, sir. Thank you so much for your inspiring and insightful session. And your blend of industry experience and deep learning expertise gave us very valuable takeaways and fresh perspectives. We truly appreciate your time, sir, and we truly appreciate your guidance. Thank you so much, sir. Thank you so much.
Thank you. Thanks all. Okay, thank you.